If you have been following along with our recent deep dives,
Yeah.
we've really been building a solid foundation by looking at three foundational industry-level engineering problems.
Right, the core pillars.
Exactly. So, problem number one,
Mm.
we established exactly how data varies and how it infers patterns from the real world. Then, problem number two, we spent a lot of time understanding how data actually lives in a high-dimensional space, which honestly is a completely wild concept once you really start to visualize it.
It really is. It breaks your brain a little at first.
Yeah. And then problem number three, we figured out how that specific space transforms mathematically. But today, we are hitting the wall that every single data scientist, AI engineer, and machine learning practitioner eventually hits.
The big one.
The big one. We are posing the master question that bridges all of these previous problems together. We know data varies, we know it lives in a space that transforms, but how do models actually learn to make sense of this?
Right, how do we get from A to B?
Exactly. How does a model move from making completely terrible, totally random predictions to making highly accurate, industry-changing ones? Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
It is the ultimate question, isn't it? I mean,
Yeah.
moving from absolute mathematical garbage to a system that can translate languages, detect diseases, or, drive a car, to a lot of people outside the industry, that transition looks exactly like magic.
It totally does.
They see the inputs, they see the brilliant outputs, and they just assume there is some kind of synthetic brain doing human-like reasoning in the middle.
And today's deep dive is tailored specifically for you, the learner, to prove that it's absolutely not magic. Our mission today is to build a completely intuitive, bulletproof mental model of the fundamental math concepts required for machine learning, data science, and AI engineering.
Absolutely bulletproof.
If you are sitting here listening to this and you have a basic understanding of Python, maybe you know how to write a function or a while loop, but you have absolutely no prior machine learning or AI experience, well, this session is perfectly tailored to bridge that gap for you. We aren't going to throw a textbook at you today.
No textbooks allowed today.
We are going to build this from the ground up, moving from the intuitive analogy straight into the actual engineering reality of what happens in your code.
To set the thematic tone for everything we are going to cover today, the answer to that master question you posed, how models actually learn, comes down to one single word: optimization.
Optimization.
Right. Optimization is the core process of searching for the best possible parameters that reduce a model's prediction error. What's fascinating here is that under the hood, this entire field is purely a mathematical search. It is an incredibly mechanical, beautifully logical search process for the right numbers.
And we hear that word parameter tossed around constantly. You read headlines about massive industry models like the systems powering modern chatbots or image generators, and you hear they have billions, sometimes trillions of parameters.
It sounds intimidating.
It really does. To a beginner, a trillion parameters sounds like an incomprehensible alien intelligence. But to start building our mental model, we need to think of models simply as adjustable machines.
Exactly. Start small. Imagine you want to build a very simple, real-world model to predict house prices.
Okay, let's unpack this. So you could write a basic formula for this, right? Like price equals W times area.
Spot on. In this scenario, you input the square footage of the house, the program multiplies it by this mysterious letter W, and out pops the predicted price of the house.
Right, so if you tell the model a house is 2,000 square feet, and your W is set to multiply that by a completely arbitrary, incorrect number, your model might predict the house costs $20 or maybe $20 billion.
And both of those are completely useless to a real estate agent.
Totally useless.
And if we map this back to what that W actually represents to you as a programmer, if you are writing this in Python, W is simply a variable. It is a parameter. You define it, you assign a floating point number to it, and the program uses it. But intuitively, think of W as a physical knob on a machine.
Like a literal physical dial.
Yes, imagine an old-school stereo amplifier or a piece of heavy industrial machinery. This knob controls how strongly the area input influences the final price output. If the knob is turned up high, the area heavily inflates the price. If the knob is turned down low, the area has very little impact on the price.
So when we talk about a machine learning, we are literally just talking about adjusting this knob.
That is it.
It is turning it a little to the left, a little to the right,
Yeah.
trying to find the exact perfect setting where the output price matches the real world.
That is the plain meaning of machine learning. And this fundamental mechanical reality is exactly the same whether you are dealing with one knob or a trillion. This is crucial for you to understand as you transition into AI engineering. The act of learning is mechanically identical across the board.
It's just a massive dashboard of physical knobs.
Right, and the system is just trying to figure out how far to turn each one.
I think this is where the intimidation factor really needs to drop for people. When an industry-level AI model is training in a massive data center running on thousands of GPUs, it is just performing this exact same knob-adjusting process on a grand scale.
Exactly the same.
The Python code behind it, using frameworks like PyTorch or TensorFlow, is simply managing massive arrays or matrices of these parameters. It is constantly tweaking them, updating the variables in memory, and running the calculation again.
The only difference is the scale of the matrix multiplication. You're moving from a single variable W to a huge matrix of weights. But if the entire process of learning is just adjusting these knobs, the system needs feedback.
It can't just turn them blindly forever.
Exactly. Before a model can actually improve and know which way to turn the knob, it has to ask the most humbling question possible. How wrong am I?
It has to quantify its own failure. Let's give a concrete example for you listening. Let's say you run your Python script, and your model, with its current knob settings, predicts a house price is 60 lakh. But then you look at your data set, the actual real-world ground truth, and the house actually sold for 55 lakh.
So your model made an error of 5 lakh.
Right.
In the industry, we translate that raw error into a formal concept called loss. Loss functions are mathematical tools, essentially just Python functions you can write in a few lines of code, or import directly from a library that convert these prediction mistakes into raw numbers.
So the plain meaning is that loss measures exactly how bad the model's predictions are.
It is the ultimate scorecard of failure.
So what does this all mean? The entire goal of model training, the absolute singular focus of all this incredible computing power and electricity, is incredibly simple. Reduce this loss number.
Drive it as close to zero as mathematically possible.
Depending on the specific project you are working on, engineers need different ways to measure this failure, right?
Yes, very different ways. If you are predicting a continuous number, like our house price example, or predicting temperature or stock prices, you will typically use a loss function called mean squared error, or MSE.
And how does MSE work under the hood?
It looks at the difference between the prediction and the reality, squares it to remove any negative signs and to heavily penalize large mistakes, and then finds the average across your data.
Mean squared error makes perfect sense for continuous numbers. But a huge portion of machine learning isn't about predicting a price. It's about categorization.
Classification.
Like looking at a medical image and deciding if it's a tumor or not, or looking at an email and deciding if it is spam or not spam. You can't really use mean squared error for that.
No, you wouldn't use MSE for that at all. Instead, the industry standard for classification tasks is something called cross-entropy loss.
I've always found cross-entropy a bit harder to grasp initially because it deals with probability distributions.
It can be tricky.
Right, so imagine the model is 90% sure an image is a dog and 10% sure it's a cat. The ground truth in your data set is that it is 100% a dog. Cross-entropy penalizes the model based on that 10% doubt.
That's a great way to put it.
It forces the model to not just be right, but to be confident. If it says it's 51% sure it's a dog, it gets a much higher loss penalty than if it says it's 99% sure, even though both are technically correct predictions in a binary sense.
That is a brilliant way to phrase it. It penalizes hesitation. Without getting bogged down in the logarithmic formulas behind it, just know that different tasks require different scorecards. But the underlying philosophy remains totally unchanged. Whether it's MSE or cross-entropy, the model is still asking, how wrong am I? And generating a loss number that it desperately wants to shrink.
Okay, so we have our knobs, our parameters, and we have a scorecard, our loss. I want you to imagine taking every possible setting of our knobs. Let's pretend you have a simple model with just 2 knobs.
Just 2.
You spend all day turning the first knob to every possible number, and for every single setting, you turn the second knob to every possible number. For every combination, you calculate the resulting loss value and plot it on a giant 3D graph.
If you do that, you create a physical mathematical space. We call this the loss landscape.
The loss landscape. And the rules of this space are incredibly straightforward. The high regions of this landscape, the towering peaks and the mountains, represent bad models. These are the knob settings that resulted in incredibly high error.
You don't want to be on the cakes.
No. The low regions, the deep valleys and the canyons, represent good models with low error. The absolute best model, the industry-ready goal that you are trying to deploy to production, lies at the absolute lowest valley of this entire landscape.
If we connect this to the bigger picture, we need a way to navigate this space. I want to introduce a visual analogy that I think is the most powerful way to understand machine learning optimization.
Let's hear it.
Imagine you were standing on a massive, highly uneven mountain, and this mountain is completely covered in a dense, impenetrable fog. You can't see 10 feet in front of you.
Okay, I'm picturing it. It's foggy. I'm on a mountain.
Your goal is to reach that lowest valley, because that is where the loss is zero, and that is where your model makes perfect predictions. But because of the fog, you cannot see the entire terrain.
A lot of beginners ask, why don't we just use a satellite map? Why can't we just look at the whole equation and use algebra to instantly find the absolute lowest point?
Right, just solve for X.
Exactly. And the reality is, you actually can do that for incredibly simple models like basic linear regression. You can solve it analytically in one step. But the moment you move to a neural network with even a few hundred parameters, let alone billions, the math becomes far too complex to solve analytically. You don't have a satellite map. You don't know where the valley actually is. You have to find it iteratively.
So the critical question is, how do you get down the mountain if you are blind in the fog? You can't look around. You can only do one thing. You can feel the slope beneath your feet. You can physically feel which way the ground is tilting under your boots.
You are standing there in the fog, shuffling your feet, trying to figure out which direction pushes you downhill. Mathematically, how do we program a Python script to feel the ground? How do we turn that physical sensation into code?
Mathematically, this slope beneath your feet is called the derivative. If you remember any calculus from school, the derivative measures the rate of change. But for our purposes, the plain meaning is all that matters. The derivative tells us the exact slope of the ground we are currently standing on.
To break down the plain meaning for you listening, if you calculate the derivative and the slope is a positive number, it means the ground is sloping upwards to your right. So if you want to go downhill, you need to move to your left. If the slope is a negative number, the ground is sloping downwards to your right, so you need to move to your right. It is a simple directional cue.
But that is just in one dimension, with one knob. Real industry models have thousands, millions, or billions of parameters. You are no longer standing on a simple two-dimensional hill. You are standing in a high-dimensional mathematical space.
Which we know from our previous problem discussions.
Exactly. And in these higher dimensions, the derivative scales up and gets a new name. The gradient.
The gradient. It isn't just a simple positive or negative number anymore. It's a vector. It has multiple components. Here's where it gets really interesting.
I like to think of the gradient as an anti-compass. A normal compass points north. But the gradient vector is a mathematical compass that actually points in the direction where the loss increases the absolute fastest. It points straight uphill towards the steepest part of the mountain.
Because the compass points uphill to reduce our loss, we simply walk in the exact opposite direction.
That deliberate action, calculating the uphill slope and taking a step in the opposite downward direction, is the fundamental heartbeat of machine learning.
This repetitive process of walking down the mountain step by step is officially called gradient descent.
It is an elegant name for a very mechanical process. Any Python programmer can visualize this as a standard while loop. The core algorithm of gradient descent can be broken down into a simple four-step loop.
Step 1. Measure the loss. Ask, how wrong are we right now? You feed your data through the model and calculate your cross-entropy, or MSE.
Step 2. Compute the gradient. Ask which way is straight uphill.
Step 3. Move slightly downhill. Adjust your parameters, turn the knobs in the exact opposite direction of the gradient.
And step 4. Repeat. You just loop those 4 steps over and over again until the loss stops going down.
If we map this to actual engineering reality, if you were using a library like PyTorch, this loop is literally written in your code. You do a forward pass to get the predictions, you calculate the loss, then you call loss.backward, which computes the gradient. It finds the slope.
Then you call optimizer.step, which physically turns the knobs and moves you downhill.
Every single time that loop runs, every step you take in the fog logically reduces the error.
Assuming your step isn't too crazy.
Right.
Which brings us right back to the foggy mountain, because there is a massive catch to this process. Once you calculate the gradient, once you know exactly which way is downhill, you have to make a crucial decision. You have to decide how big of a step to take in that direction.
Do you take a tiny shuffle, a normal walking stride, or a massive flying leap.
In machine learning, this concept of step size is called the learning rate. Setting the learning rate is one of the most important jobs of an AI engineer. It is the classic Goldilocks problem.
The extremes of this Goldilocks problem are where engineers really start pulling their hair out. Let's say you set your learning rate too small, meaning your Python script only updates the parameters by a microscopic fraction each loop. You are taking incredibly tiny steps down the mountain.
Your progress will be agonizingly slow.
Agonizing. You might be running your code on expensive cloud servers for days, weeks, or even months, and the loss is barely decreasing because the model is just inching its way down millimeter by millimeter. You are burning through your AWS budget just to move an inch.
On the flip side, what happens if you lose patience and set your learning rate too high? You decide to take massive bounding jumps down the mountain in the fog. You calculate the slope, realize downhill is to the right, and you take a huge leap.
The danger here is catastrophic. If you take a step that is too large, you might actually overshoot the valley completely.
Exactly. And if you do that repeatedly, the loss actually goes up.
Imagine a programmer sitting at their desk, watching their terminal output. They start training a model, and the loss starts at 100. They want it to go down. The first loop runs, they take a massive leap, and suddenly the loss is 500.
They jumped completely over the lowest valley and landed high up on the opposite wall of the mountain.
The next loop runs, the gradient points back toward the valley, they take another huge leap, and now the loss is 2,000.
They're bouncing side to side, higher and higher up the canyon walls, and the model is failing spectacularly.
Eventually, the Python script will literally just print nan, not a number, because the math exploded. The numbers got so large that the computer physically couldn't store them in memory anymore.
That happens all the time in practice. That bouncing phenomenon is exactly what an exploding gradient looks like when the learning rate is too large. So the engineer's goal is to find that just right learning rate. A step size that is large enough to make efficient progress down the mountain, but small enough to safely settle into the lowest point of the valley without jumping out of it.
Is it usually just one static number?
In the industry, we rarely use a static learning rate. We use learning rate schedulers, which start with larger steps when you are high up on the mountain, and then slowly reduce the step size to tiny shuffles as you get closer to the valley so you can gently settle into the lowest point.
Okay, so we have our while loop, we have our gradient compass, and we've carefully selected a reasonable learning rate. We're slowly but surely navigating down the foggy mountain. But there is another major bottleneck we have to address, and it comes from the hardware reality of the industry.
The big data bottleneck. In a perfect, theoretical, mathematical world, to compute the absolute perfect gradient, the flawless, most accurate compass reading of the slope beneath your feet, you would need to look at all of your data points at the exact same time.
All of them.
All of them. You would feed the entire data set through the model, calculate the total average loss for every single piece of data, and find the true gradient of the entire mountain.
But look at real-world data sets. You might be working with tens of millions of samples. If you have a massive data set of 50 million high-resolution images, trying to load all 50 million images into your computer's memory, run them all through the model, and calculate the total error just to take one single step down the mountain, it is impossible.
Completely impossible. Your GPU has a physical limit, VRAM, video RAM. You might only have 16 or 24 gigabytes of memory. You physically cannot fit 50 million images into the GPU at once. Computing the whole mountain at once is completely unscalable.
The industry's solution to this hardware limitation is a brilliantly practical shortcut called stochastic gradient descent, or SGD.
The word stochastic essentially means random. Instead of using all the data to calculate a perfect slope, we estimate the gradient using small, random batches of data. Usually 32, 64, or 128 images at a time, whatever fits comfortably in your GPU memory.
Bring back our mountain analogy for a second. Standard gradient descent is like freezing time, deploying a fleet of drones to perfectly map the entire massive mountain, calculating the optimal geological downward angle, and then taking one flawless, perfectly calculated step.
Which takes forever.
Right. Stochastic gradient descent is entirely different. Instead of mapping the whole mountain, you reach down, pick up one small rock at your feet, examine the slope of that specific rock, and quickly take a step based only on that rock.
Because you were only looking at a small, random batch of data, that one little rock, your gradient calculation isn't perfect, it's just an estimate. The rock might be tilted slightly differently than the actual massive slope of the mountain. Because of this, your path down the mountain isn't a beautiful, perfect straight line into the valley. It zigzags. It
It
wobbles.
looks exactly like a drunken walk. You are stumbling down the mountain, swaying a little to the left, a little to the right, sometimes taking a step that actually goes slightly uphill for a second before correcting itself because the specific batch of data you looked at was a bit weird or noisy.
But here is the big takeaway and why this is the industry standard. Taking thousands of these fast, slightly inaccurate, wobbly steps is vastly faster and more efficient than taking one perfectly calculated, incredibly slow step. Mini-batch SGD allows your model to update its parameters thousands of times per second.
Yes, it's a drunken walk, but it is a drunken walk at warp speed.
Exactly. You reach the valley exponentially faster than the slow, perfect method.
Okay, the drunken walk gets us down the mountain faster. But wait, what if the mountain has giant craters in it? We've been imagining this foggy mountain as a relatively smooth slope down into a valley. If I'm taking random wobbly steps, won't I just fall into a ditch and get stuck?
This raises an important question. Real-world lost landscapes are rarely smooth. They have small bumps, little ditches, rocky patches, and completely flat plateaus, what we call saddle points. If you are doing standard gradient descent and you step into a tiny little pothole on the side of the mountain, the gradient at the bottom of that tiny pothole is 0.
Because it's a ditch, it briefly flattens out. Your model's mathematical compass stops spinning. It thinks, the slope is 0. I must be at the absolute lowest valley of the entire mountain.
And it stops learning. It gets completely stuck in a tiny ditch halfway up the mountain.
To solve the problem of uneven terrain and getting stuck in these false valleys, engineers introduced a concept called momentum. To visualize momentum, imagine you swap out your boots. Instead of walking down the foggy mountain, you take a heavy bowling ball and you roll it down the hill.
Because the bowling ball is heavy, it builds up physical momentum as it rolls. If it hits a tiny pothole or a small bump, it doesn't just stop instantly like a person walking might. Its accumulated speed and mass force it to roll right up and out of the pothole, blasting past the small bumps and continuing its journey down the larger slope toward the true valley.
Hold on, though. If the bowling ball is incredibly heavy and builds up all this massive speed so it can blast through a pothole, doesn't it run the risk of rolling right past the actual lowest valley at the bottom of the mountain, too? Couldn't it just fly out the other side?
That is an excellent point, and that is a real issue called overshooting due to high momentum. In the actual math, we introduce a friction coefficient, usually called beta. It decays the momentum over time, so the ball eventually slows down and settles. But mapping this heavy bowling ball trick to the plain meaning in our code, momentum simply gives the optimizer a memory of its previous steps.
It remembers the direction it has been traveling.
By maintaining this mathematical inertia, it keeps moving forward even if the immediate slope briefly flattens out or becomes confusing.
If you look at any professional machine learning code base today, you will see optimizers with names like Atom or RMS-prop. All of these industry-standard optimization algorithms are built directly on this exact trick. They combine the fast, zigzagging steps of stochastic gradient descent with the heavy, bump-crushing inertia of momentum to speed up learning and ensure the model actually finds the best possible parameters.
This brings us to a really fascinating philosophical shift regarding the types of landscapes we are actually dealing with in modern AI. The shape of the mountain changes drastically depending on the specific model you are building. Some optimization problems are wonderfully easy. For example, if you are building a simple linear regression model, the landscape is incredibly forgiving.
We describe the landscape of linear regression as a perfect bowl. Imagine a completely smooth, perfectly symmetrical ceramic bowl. No matter where you drop a marble on the inside edge of that bowl, gravity will pull it down and it will eventually settle at the exact same spot, the absolute center at the very bottom.
In mathematical terms, this is called a convex problem. A convex landscape has exactly one valley. There are no fake valleys, no confusing terrain. If you follow the slope downwards, you are mathematically guaranteed to find the single best set of parameters.
But the reality of modern AI is that we are rarely dealing with perfect bowls. We want to solve much harder problems like image recognition or natural language processing, which require complex, deep neural networks.
And when you use a complex neural network, the lost landscape distorts. It is no longer a perfect bowl. It transforms into a vast, jagged, chaotic mountain range.
There isn't just one valley anymore. There are thousands, maybe millions of different valleys, all at different depths, separated by towering peaks and confusing ridges. These are known as non-convex problems.
If you were an engineer standing in the fog in a non-convex mountain range, how do you guarantee you find the absolute lowest valley in the entire world when there are thousands of deep canyons all around you? Here is a crucial industry reality that often shocks beginners. You don't.
You give up on perfection.
You accept finding good enough valleys. If your neural network descends into a valley that is deep enough, your loss will be low enough that the model makes highly accurate, incredibly useful predictions in the real world. You might not have the literal mathematical optimum, but you have an industry-ready model that generates millions of dollars in value. Optimization in deep learning isn't about perfection, it is about extremely effective navigation.
And what's wild is that because there are so many different valleys, you can train the exact same model architecture twice with the exact same data.
Yeah.
But because you started dropping the bowling ball from slightly different spots on the mountain, different initializations, they end up in completely different valleys.
They might both have a 95% accuracy rate, but they behave differently. One chatbot valley makes it polite, another valley makes it slightly more snarky. Same loss, different internal parameters.
That perfectly synthesizes the entire big mental model we set out to build today. If you take away just one thing from this deep dive, let it be this. Learning in machine learning is simply navigation in space.
Models start by measuring error. They ask, how wrong am I? And calculate the loss. Then they detect the slope. They calculate the gradient to figure out which way is uphill. Then they move downhill. They take a step governed by the learning rate in the opposite direction, and then they repeat that loop. This mechanical navigation is what turns a useless pile of random parameters into highly accurate, industry-ready models.
To really solidify this for you, let's do a quick translation drill. We're going to frame this as a survival guide for your first engineering stand-up meeting. Let's say you just got hired. You are sitting in your first sprint planning meeting, surrounded by senior AI engineers. They start throwing around dense expert jargon. I'm going to play the senior engineer throwing out a jargon phrase, and you translate it into the plain meaning we've established today. Ready?
Ready. Let's do it.
Okay, here we go. Jargon phrase number 1. The model minimizes the loss.
Translation. The model is simply adjusting its parameters, turning its knobs to reduce prediction mistakes based on the scorecard we gave it.
Jargon phrase number 2. We optimize the network using gradient descent.
Translation. The model repeatedly calculated the slope of the error and took a step downhill in the loss landscape.
Jargon phrase number 3, and this one comes up all the time. The training curve is noisy.
Translation. We are using stochastic gradient descent. Because we are looking at random, small batches of data instead of the whole data set, our path down the mountain is zigzagging. It's the drunken walk, so the graph of our error jumps around a bit as it goes down.
And final jargon phrase, we need to add momentum to the optimizer.
Translation. We gave the optimization algorithm the physical inertia of a heavy bowling ball, so it pushes through small bumps and doesn't get stuck in tiny, fake valleys on the lost landscape.
Perfect translations.
To wrap all of this up with a final provocative thought for you to mull over, the most profound realization in AI engineering is accepting that machine learning models do not magically discover patterns. They do not possess intuition. They do not think in any human sense of the word. They mechanically, relentlessly search for better parameters. It is an algorithmic pursuit of the lowest ground.
Now you understand the exact tools of this search. Loss measures the mistakes. The gradient points uphill. The learning rate controls the step size. And momentum pushes through the bumps. Together, these beautiful math concepts are the exact mechanism that allows lines of code to actually learn from data.
It's all just math and code.
But as always, solving one engineering problem usually uncovers another one. Today we saw exactly how models descend the lost landscape. But deep learning introduces a totally new challenge. In a deep neural network, you don't just have one set of knobs. You have layer upon layer upon layer of knobs. The gradients we talked about today must somehow travel backwards through many layers of a massive network.
It's a huge coordination problem.
Exactly. How does a signal of failure at the very end of the model mathematically flow all the way back to the beginning? In our next lecture, M6 How Networks Flow, we will explore backpropagation and learning in neural networks. We'll see exactly how gradients move through deep networks so that complex AI systems can learn.
It's going to be a great session.
Before you go, we highly encourage you to try that translation drill exercise yourself. The next time you are looking at a piece of sample ML code or an article about AI training, mentally translate the jargon into the foggy mountain, the drunken walk, and the bowling ball. It will dramatically change how you read technical documentation. Rate any questions or aha moments you had in the comments below. Make sure to like, share, and subscribe to the 60 Seconds Academy AI and ML channel so you don't miss the next deep dive. See you next time.